Hello and welcome to the New York, New Jersey Trail Conference. My name is Pat Gallagher. I'm the Advancement Director here. We're very excited to have you all here in the room and to those of you joining online for this very special presentation from our distinguished guest. For those of you who may be new to the Trail Conference, our organization is a century-old volunteer-powered organization that builds, maintains, and protects over 2,000 miles of public trails and surrounding lands across our region. Together with our partners, we strive to ensure that the trails and natural areas we share are sustainable and accessible for all to enjoy for generations to come. It's with the support of the community and folks like you that make our work possible. So we'd like to send a big thank you to our volunteers, members, and donors joining us today. Before we begin the presentation, I'd like to point out for those of you on Zoom, you will remain muted during the presentation and we will be monitoring the chat. So we hopefully will have time for a Q&A at the end of the presentation and we will return to your questions at that time. So please hold off on asking any questions in the room until that time as well. So now to introduce our speaker. Dr. Alexander Gates is a distinguished service professor and former Vice Chancellor at Rutgers University, Newark. He has been in Rutgers University for 37 years and served as Chair of Earth and Environmental Sciences for 20 years. Dr. Gates earned his PhD from Virginia Tech in Structural Geology with a specialization in faults. Gates was a senior scientist with the New York Geological Survey in charge of the Hudson Highlands. His team has produced 8 bedrock geology quadrangle maps of the region. Gates also has extensive experience in geoscience and STEM education, especially for students from minority groups, underrepresented in STEM. He is the author of 9 books and 82 professional papers and has edited 11 professional volumes. Gates has received 26 professional awards. So without further ado, please welcome Dr. Gates to the podium.
Okay, well, thanks everybody for having me. So a little bit about myself. I grew up in Rockland County. So I went to Spring Valley High School. And when I was a teenager, I used to go hiking up in Harriman State Park. And I said, I was graduating and I said, I got to find me a job where I can walk around the woods and get paid for it. So that's what I did. So I've walked around the woods a lot of places. I calculated once that I've walked out 750 square miles through woods from Maine to Alabama. Now, and I also worked in Colorado. So I got, so I did all this work in Harriman where I got started. And, after I got my PhD, I applied to places all over the world. And where do I wind up? 40 minutes from where I was. And then I worked for the New York State Survey. Where they put me in charge of? The place I hiked in when I was a kid. So anyway, everything goes. I guess what goes around comes around. Anyway, that's what it is. So I decided I would dress up in the outfit that I used to wear when I worked for the New York State Survey, so I could walk around in the woods and not get too much hassle on it. To tell you the truth, all you can get is a patch there. So I got this shirt, I put this on, I put everything else on. Then everyone lets you on their property. Otherwise, if you look like you're just walking around, they don't do it. So anyway, so I figured I'd wear my field outfit that if anybody has seen me doing work in the woods, this is what I would look like, except a little younger. Okay, so next slide, please. All right, so let me show you some of the stuff. As he said, I have a team that I had put together and we mapped 8 quadrangles, 7.5-minute quadrangles. Those are the old quadrangle maps that they used to use. I don't know if they still do. I think everything's going metric down in the area. And so that means we walk, you guys all walk on trails, means we walk through everything. You walk to where you can get to the rock. So we bushwhacked our way through the area, through 8 of these. And as you can see, if you see all the little dots on there, those are places that we've been. Okay, so we took measurements on all of those places. Through this area, we have other ones, there's, I guess that's still Monroe, but I've done Maybrook, I've done all the way over to the Hudson River in this direction. So mostly to the north, we've done even more than this. And, but you can see that's the kind of coverage we have. So all of the colors on there are different rock units. And I will be showing you close-ups. I'm not going to go through what each of the rock units are, but that is the most modern map of the area. In addition, I'll point out, in addition to all the colored stuff on there, these harder lines, the darker lines are faults, and some of those faults are active. So we actually, have been studying these for a long time, and so that earthquake that happened the other day was on one of those kind of faults. Okay, so basically we've actually seen them. All right, next slide. Okay, so what I'm going to talk to you about today is they wanted me to talk about the basically that we have a chunk of South America in the Hudson Islands. So I came to talk to you about that. So what I'm going to do is I'm going to show you the whole geology of the area and show you how that fits in, and then what kind of plate tectonics had to have occurred to get us a piece of South America stuck in Harriman State Park. And I'll show you where that is so you can go get a piece of it if you want. And anyway, so what I will show you is that we have a bunch but these are all metamorphic rocks now, and I'll show you why they are later. But they started out as a volcanic arc. So this would be something like that you would have in, say, the Aleutian Islands, was what the original part of some of the rocks are. They're volcanic, and those are really the origin of the iron deposits that are mined all over the place. We also have some sedimentary rocks that form next to these volcanic rocks that would then be metamorphosed, and I'll show you what those look like. We had a continental collision. Everything was deformed. I'll show you how the deformation worked. Got metamorphism. Everything was cooked up to almost to the point of melting, that much. We have a piece of Amazonia, which is from basically under Brazil these days, that's stuck in Harriman State Park, and I'll show you why. And then I'm also going to show you that there was a big strike slip faulting, which is like what the San Andreas does. It slides sideways. That happened. We had plutons, and then how most of our iron things that we mine were made. Next. Okay, so as I said, we have the basic rock units, our metavolcanic gneiss, which started out as these are all metamorphic rocks. They started out from the volcanic rocks. We have metasedimentary gneiss, which started out from shales and sandstones and limestones. We have another unit called the Quartzofeldspathic gneiss, which we are still fighting about with some of my friends, whether it started out as a sedimentary rock or an igneous rock. Hard to tell once they're cooked up almost to melting. So those are the main rocks. Next. Okay, so here is a map of an area in here, and so you can see where some of the names are on it. Now I put on the red line is the New York State Thruway. See, it's labeled, and this is where Route 106 comes through up. So over here would be say Little Long Pond and Kanawaki and things like that. And here's where the two cross. So this is, and then down this way would be Sterling Forest. So basically in here you can see some of the units. We have the purple unit is the metavolcanic unit. The green is these metasedimentary units. The yellow would be this Quartzofeldspathic gneiss. You see my colleague decides to make it a granitic gneiss, even though I said we're not sure. There's intrusion of these granite sheets into here. And then there's these other strange looking things, which are basically, they are very deep fault zones, otherwise known as myelinite zones or shear zones. So there's a lot of those that cut through. You can see all these features mean that there's a lot of folds in the area. Every place you see the two arrows going in all directions, that means those are folds of the rocks. And so that's the basic of these in the area. So you can see what we're going to see. So I'm going to show you some of this stuff, including the granite sheets and everything else. So next. Okay, so first thing, I'll show you what the metavolcanic rocks look like. So when you're out hiking, you can take a look. There's a place on 106 where Little Long Pond and Kanawaki almost touch each other. That's where this is taken. And you can see it has very dark colored bands mixed in with light colored bands. Now we've done I have a colleague of mine who's a geochemist who did the chemistry on these rocks for me. He's at Montclair State University, and these come up dead giveaway island volcanics. So in other words, these would have come out of the Aleutians, out of the volcanics, out of the Aleutians. These are explosive volcanics that would have been taking place at this time. And being that means we had to be in a situation where we have two things pushing together to get those kind of volcanic rocks. So they come up nice, perfect. Okay, now you can see they're nicely banded. That means they're nice, GNEISS. And so that means this isn't the whole thing. And we're going to take a close look at that little white spot over there. Next slide. And you can see here it is. And what has happened in here is when these rocks underwent metamorphism, which was during the collision with another between when then North America and South America, this thing got buried so deep that and heated up so much, the rocks started to melt. Okay, so we're at the edge so deep down. So if you were to kind of think about what this is, if we were to erode away 10 kilometers or maybe even more, probably closer to 15 kilometers of rock from under the Himalayan mountains right now, that's what it would look like. Okay, so it's so hot. These are under such high mountains that they start to melt. Okay, and so these are dead giveaways when you have these little net veins. You see they kind of make like a net pattern. That is a dead giveaway for something called a migmatite, which is a mixed rock between a metamorphic rock and an igneous rock. And so that's just to show you how hot this stuff got. All right, that's why we have all these crystalline rocks in here. Okay, so that's a partial melting of these volcanic rocks. Next. Okay, the next thing we have are these metasedimentary rocks. So the metasedimentary rocks come in several types. So we have what's called a metapelite, which started out as a shale. Okay, and these are going to give you all kinds of wild minerals. Okay, when you start them out that way. Next thing is what are called calcsilicates. These are marls. If you go down to the Jersey Shore now, they have these calcareous muds. Those we have as well. We have some quartzite up here, which is going to turn into, 100% quartz, like sand from the beach, and then limestone. And limestone turns into marble. The sandstone on the beach turns into a quartzite. And so we get sequence of these all over the place in those areas marked metasedimentary rocks. So these were originally sedimentary rocks out in the ocean that then again were cooked up so hot that they metamorphosed into something and then partially melted. So what I'll show you in here, and nobody's allowed to take this rock away from me, is you can take a look on here. This is an area right out on Seven Lakes Drive where you get these big garnets all stuck in quartz. And so I show people this rock and I say, but you can't take it away because not that much of it. But so that is when you get these metapelites, they get lots of garnets in them. And these are kind of pinky purple garnets, which a lot of people see the bright red garnets. These are a little different in chemistry to get to that. In addition to that, we get other wild minerals, sillimanite and cordiorite and things like that. Anytime you want to tell one of these, you'll see a lot of mica in it. Now, we only get, there's two kinds of mica. There's a white mica and a black mica. And black mica is called biotite. All the rocks in here, when they shine up in the sunlight, they glint. They're all biotite. Okay, and the reason is that the rocks got so hot that they cooked off all the muscovite. So it's one way we can tell that this rock was so close to melting was that in these rocks, which should be loaded with muscovite, they don't have any. That means you almost got them to melting. It was so hot. Okay, so this is just one picture of a sedimentary rock, the nice one with some garnets in it. Next. Okay, so what I'm going to show you now is we did some dating on these. So what we have in these, all these rocks, whether igneous or even in sedimentary, but metamorphic rocks, is a mineral called zircon. Okay, and zircon is important because it will capture, uranium and lead at a certain percentage when it starts, and then it'll start to decay. So it's like it turns into like a little timer. So as soon as you crystallize it, from either igneous intrusion or in crystallizing it in metamorphism, it starts to decay and it records the ages of how old the rock is. Okay, and so these rocks that we've been talking about so far are about 1 billion years old. So these are old rocks. Okay, so what we have in here is these are the sedimentary rocks. So as I said, we had a bunch of metasedimentary rocks. And what we wind up with is some up in the 1.4 billion year range. And if you go west of here, in places like where the Franklin Marble is, in that part of New Jersey, the rocks are more 1.3 to 1.4 billion years old. So all those sediments were probably being eroded from there. And so all the way down, we're going to find some other rocks you'll see later at about 1.2 billion years old. But the big thing happened between about 1.5 and 1 billion, which you can see all this stuff in here, is when the metamorphism took place. So it's recording some of the erosion, but also that metamorphism. So we know that when the metamorphism and all that deformation took place was about at 1 billion to 1.050 billion. So about that 50 million year period in there is when the metamorphism took place. Okay, so we'll see that on all the rocks. The other parts might change a little. Excellent. Okay, so here is so that was the sedimentary rock. Here's what the Quartzofeldspathic gneiss looks like. Okay, and so you can see it's very, it's got a lot of banding to it. It'll have, these are pegmatite veins that cut through, and so those where it melted locally. But this strongly banded stuff, you can see it all on the tops of the ridges. So it tends to be very tough. You walk along on those ridges, where the boulders are all sitting from the glaciers, you look down, that's what you'll see. Okay, so the problem with us now is because it's been deformed so much to just into a gneiss and layered and cooked up, can't really tell what it was originally. So we have a big argument going on. My view is that these were what are called volcaniclastic rocks. So you had volcanoes there, and it was just being eroded down into these sedimentary piles. That was that. My colleague, who is at SUNY Oswego, thinks they're all intrusive, so that they're big plutons of magma. So we still haven't worked that out, but we always fight about it over a beer every once in a while. So anyway, but that's what we have, these Quartzofeldspathic rocks. So let's see the next one. Okay, so here's some pictures of zircon. So you can see they kind of have some banding in here that shows you different ages of growth. And then that white on the outside, that's the metamorphic edge put on top of these original grains. So what you do is you go and use a mass spectrometer, and which measures the ratios of very close together things, and we plot them against each other. So that's what we did before. This is lead-206 and uranium-238 versus lead-207, uranium-235. You do the two ratios, and then you can see what the ages are. So basically, you start out with a certain amount of uranium, and as it decays, it'll decay to lead. And so by looking at how much it's decayed, we can tell how old it is. Okay, so this is what you saw before. Now, these Quartzofeldspathic rocks come in this whole big area in here, and so we have down here is the metamorphic ages, 1 to 1050, a billion to 1050, and they have a bunch of ages up around from about 1200 to about 1150. And when we did the igneous rocks, the metavolcanic rocks, they come up the same. So they're about the same age as the metavolcanic rocks. That, I think, is when we had active volcanism. Okay, so we had all this active volcanism, and then bang, they crashed, the continents crashed together in that low part. So that's kind of the two parts of why we have two areas. Next. Okay, so here, now I can wave my arms a little and show you that's what your geologists do. When you're about to put the model on, it's a lot of arm waving, okay? Because there's so many missing parts. Okay, so here is basically, I took this from another picture, but I just put a bunch of things on to show you where we are. So North America would be over here, okay? We would have where the highlands are mostly coming from, and there's your Amazon or Amazonia, which would be South America over there. Okay, so what's happening is the green is ocean crust. Okay, so this is what you have on the bottom of ocean. When you push two things together, the ocean crust goes under because it's denser, right? So you start squeezing these plates together and the ocean will go under. So as I said, the Aleutians basically works that way. The Pacific Ocean plate is being subducted, that's what this is called, subduction, underneath the Aleutian Islands. Same thing was happening back here. The highlands, we had the subduction going on, we had volcanics. Here's our volcanism at the top. I'd say the sedimentary rocks coming down the sides of those volcanic rocks would make the Quartzofeldspathic gneiss. Once you get out into the water, into the deeper ocean, that's where you get the Metasedimentary rocks. So that's where we're putting these together. Now, there's a model, not sure if it's true or not, but the model right now that's being accepted is that we had what's called back arc basin. And so if you think about Japan, you get that Sea of Japan between Japan and China, it's pulling apart a little bit. And it gets, because it's so isolated, you can put out all kinds of metals. And so the model right now is that we put all this iron out in this area right here. And so the reason that we have so much iron in the highlands would be because it formed in this back arc basin. Okay, so if you want to think about these narrow basins, you might go to the Red Sea now, which is a narrow basin. It's full of all kinds of metals. They're all being deposited on the surface. So that's why they think, because we have an awful lot of iron up here in the highlands. Why is it there? Right now, that's what they think the reason is. Okay, but again, this happened 1 billion years ago. A lot of things missing. Okay, so this is our model that we're putting together. So I've shown you some of the stuff that was in here. I'll show you some of where the iron goes in a minute. North American stuff would be west of here. And then we got to take a look at Amazonia, because that's going to come in and crash into North America. So this is about 1.180 billion years ago. Next. Okay, so here it is. So just going along and mapping. And so you can see where that is because I took the picture so you can see exactly where we are, right? So there's Perkins Drive. And right where you come up, you're coming up the Palisades Parkway and it says, take a whatever to go down to Bear Mountain. You kind of come around that corner to the right there. And before you get to the Perkins Drive exit, there's all these rocks that kind of go this way. And these are all layered. They're started out sedimentary rocks, and they are all layered, looks like sandstones and shales. They started out as, and now of course they're cooked up to the gills. Okay, so we went out here and we were taking samples and we were dating to see what age the rocks were. So we went here and got a sample list and okay, let's date it. We'll see what it looks like next. So here's some of the pictures of the zircons. Those are little grains that we got. We ran you run these in the mass spec, and we got that. Okay, so you will see, in the beginning part over there at 1 billion, we know that. we've seen that before. All the way up to 1.4 billion. Yeah, I've seen all of these. We've seen in the sedimentary rocks, the one at the 1.2 billion, that big peak there. Yeah, that's all the volcanic rocks. But what on earth is all this stuff all the way up here? We got ages all the way out to 2.8 billion years old showing up in these rocks. Okay, which is, nothing is like that. Is that old around here? I don't even think in the Appalachians anything that old. So we had to kind of search around for where it could have come from. And what this age spectrum matches is from Amazonia, which is basically the core of South America, and it's in Brazil. So this is the evidence that those rocks over by, on the east side of here, over by, by Bear Mountain, aren't from North America originally. They were from South America, from Amazonia, that when they crashed together, a piece of South America was left behind when South America pulled back apart again, a few millions of years later. And that's it, and that's what it is. So that, we can't see anything else. There's no fossils. This stuff's all been cooked to the point where it's almost melting. There's no anything else. But when you see zircon grains looking like that, yeah, it can't come from here. Okay, so that is my evidence to tell you that that's Amazonia. Next. Okay, so how did this work then? Well, what happens is when you have a continental collision, you had your subduction that started before when the ocean crust is going underneath the continent to begin with, and all of a sudden you run out of ocean crust, and the two continents hit each other. Okay, and so here would be Amazonia over on the left-hand side, and here's North America on the right, and bang, the two things come together, and you put up this mountain range, because once it's like a car crash, everything smashes together, it lifts it up, and we get these huge mountains. Okay, and so today, if you were to look at this, as I said, the Himalayas are from the collision of India with Asia, where India was subducting underneath, and bang, the two hit together, and you put up this huge, Tibetan plateau and the mountains. The Zagros over in Iran are from a collision as well. So, and anytime you see mountain ranges, they're mostly from collisions. Okay, and then they slowly erode away. So here was this huge collision. So what I'm going to show you about the collision is that normally when these rocks all get crumpled up. Okay, so normally when we crumple up rocks, they kind of fold up like that on the top. So you see the kind of the arch shape fold. But because there's so much weight on these things at the bottom, they can't go up. They have to only go sideways because the weight is too much. So anytime you want to fold, that's where you're going to do it. But that's where you really thicken up the crust. So to make mountains, you really have to do something like this at depth. Okay, and so can we see that in next? Okay, so here is basically what I'm saying is what happens in this is, if you slide a rug on the floor, the rug doesn't have enough strength in it to go up. It does this, right? But now look at the height difference. The height over here was only that thick, but now look, it's all the way up to here. So I've really thickened up my rug on the floor, or if I was going to do this to rocks, it's crustal rocks. So that's how I'm going to build that crust so thick that I can put mountains up. Because you put mountains up, it means the crust has to go way down into the mantle. So reality is underneath even though we only see 30,000 feet, up on sitting in the Himalayas today, the crust in there is 80 kilometers thick. So it sticks way down into the mantle to get any mountains at all. Okay, so I'm going to show you what it looks like in there next. Okay, so you're driving along the thruway, okay, and you look out the window, and you can look here, you can see I drove along the thruway and looked out the window, and you see all the rocks are just lying flat as a pancake. It's almost like they're sedimentary rocks. And here's a close-up of what they look like. So you say, well, why are these rocks sitting down flat like that? You'd think they were really deformed. They should be up high. No, these are the bottom of those folds that do that. They're called recumbent folds. They lie on their side, so it's recumbent. And so that anytime you go through the Harriman State Park or the Highlands in this part of it, and you see the rocks lying flat like this, these ridiculous metamorphic rocks, see all the banding on here, it's all nice. You see them sitting there, they're at the bottom of one of these big things, they're called naps, but they're right at the bottom of one of these naps. You go to the Alps, and they have these huge folds that look just like what I showed you, or you take a cruise up in Norway on the fjords, huge folds like that. They're all showing you that they're at the bottom of mountains. But you can see that's where these come from. All right. So you drive your car along and you see the rocks doing that, you're in one of these. Okay. So that's the first part of it. Next. And you can see, if you're lucky, you can find places where you'll see the end of the fold. So this right here, out on Route 106, just west of Kanawaki, east of Kanawaki Circle, there's the bottom of one. Okay, so you can see the flatline stuff coming in like so, but all of a sudden there's that fold showing you that that's where those, as I said, they're called naps, Renville naps. And that's what built the height. That's what made those mountains so big, is these kind of folds. But mostly you drive along and it looks flat as a pancake. And you know, because you drive down south into the Appalachia or out to Pennsylvania, and the rocks are all doing this. Why are they all flat here? That's the reason. Next. Okay, so and then when these things start to build up like that, they start to compress and heat. You know, it pushes stuff down and heats it up, starts to melt it. So you can see I've got this nice hand sample of this. So you can see here's the low flatline stuff. Notice it goes into one of those naps, and look what comes right in along here. It's a big intrusion of granite. Okay, these are called tectonic surge granites. They occur at the peak of making a mountain because it gets so thick that the rock melts and intrudes in along here. And so you get these granite sheets, okay, next, that come in like that. Now, here are the granite sheets. And so they go up along all over the place. You can see these long linear granites. Now, if you have, any of you have ever been to Claudius Smith's den? Okay, so you walk up the Claudius Smith's den and there's this cliff, right? And if you look close, it's all granite. And if you look on the sides, you can see chunks of other rocks in the granite. So that whole ridge is one of these granite sheets. Okay, so you can see these out in the woods. You know, I think that one's down here, but big ones all over the place, these long, thin granite sheets, because they were right at the peak. It got so hot, they melted up and the little granite just slid right along those folds. And that's why they're where they are now. Okay, next. Okay, so well, let's put this all together. This was the biggest mountain system ever in the history of the world. Okay, you can see where this is all kind of, I pulled this off the internet, so you'll have to pardon this. It's upside down. Here's Hudson Bay. This is North America. This is South America. We're sitting about here, maybe at the L in Renville. This is where those two things came together, but there were other things that collided at the same time. So this red area, which goes from all the way down across Antarctica to a chunk of South Africa, all the way through North America, and it goes all down into the Llano uplift in Texas and down into Mexico, and it comes all the way up through North America and across to Baltica, which is Norway and that area. It went through all of the continents on the entire planet. And so it was as high as the Himalayas and much longer, okay, much bigger. So this was the biggest, longest mountain system ever in the history of the planet. So what we are looking at now, when you go out and look at those rocks, you are looking at the bottom. We've eroded away all this stuff. We're 15 kilometers deep underneath those tops of those mountains, maybe even 20. That's what you look at with the rocks. Okay, so that brought together this supercontinent. Okay, and this was, I don't know if you've heard of Pangaea, the supercontinent. This was the one before Pangaea. So the reality is what they think these days. Again, since we weren't there, we can only postulate, but every 500 million years, all the continental mass comes together and makes a supercontinent. Okay, and then it breaks apart and then it comes back together again. So basically all the continents are back and forth. So this one was, you know, 1 point whatever, billion years ago anyway, something in that ballpark. And then it's broke apart and it came back together again about 250 million years ago. You can see now our continents are about as spread apart as they can get. It'll take another 250 million years to get them back together. But so that's the idea, is they're all in cycles. So you can see this is the last big supercontinent before Pangaea. Next. Okay, so what happens after that? All right, so this is a couple of years ago. I think it was like 2002, so I was much younger. And I got on the cover of the New York Times. They had full color thing of me standing on this rock. Okay, and this is my Rosetta Stone rock for how to figure out all of what the heck is going on in Harriman State Park, in the whole of this part of the Highlands. And so here's the picture. And so you can see there's this rock down here, which is called diorite, and then something else is going on there, which we call a xenolith. Okay, it's a xeno, means comes from someplace else, lith rock. Okay, and so the diorite is an igneous rock. All right, and diorite is like a granite, except a little more what they call more mafic. So it's a little darker in color, but nonetheless, this is what it looks like if you look at it. And so these guys, these big things here are about 2 centimeters across. This is big. This sits right out on Seven Lakes Drive, across from Lake Tiarati. There's an island out, as you drive by, there's a rock island that's pretty close to the shore. It's right across from that. Okay, so I take and you might see me taking my classes there because I don't exactly look at it. So you can see this diorite, and here you can see there's all kinds of wild mineralogy going on. So the brown in there is like the higher temperature mineral, and then there's a green mineral on top of it. There's a little bit lower temperature, and then the black you can see surrounding the green, and that's a little bit less. So you can see all the way down the cooling that took place. So this is really a great rock. Okay, I would love to take pieces of it to give to students, but I'm not going. Anyway, so here's you can see this rock came in, and diorite, as I said, it comes in as a magma, and it's about 1,000 degrees centigrade. Okay, so this is hot stuff. All right, now let's take a look at what happened. How is this relation with this xenolith and this diorite? Next. Okay, so just as a little background on it, the magma comes up into your surrounding rock, which they call country rock. Okay, and if you have a xenolith, it is a piece of the country rock dropped into the magma, and if it comes from the roof down, you call it a roof pendant. Okay, so I'm going to show you that the diorite was the magma, there was some country rock was the gneiss, and there's that roof pendant dropped in. And so some cool stuff happens to that. Next. Okay, so here it is. Look at this piece right here. Here is a close-up of that roof pendant. Notice it's got the gneissic layering to it. So it was already squashed under the mountain belt, metamorphic, deformed prior to the intrusion of this diorite, right? Because diorite doesn't have any layering in it. If you squeeze it, you have to layer everything. I only layered this one. So that means this was done being layered when this intruded. Okay, now when this dropped in, you can see how the layering kind of sweeps back in like this. As you can see the blue, it dropped down into this liquid. And it's made that other stuff kind of sweep, all of the layering, it kind of gets all squiggly up in here, but when it gets close to the edge, it just sweeps. And so that's like, it's dropping down, it's pulling it back as it drops down. Now, the other thing you can see that's kind of neat about this is there's this white band along the edge of the xenolith where it touches the diorite. And this is granite. And because this was so hot, it was 1,000 degrees centigrade, it melted the gneiss. So right along the edge, you've got some melt against this xenolith. Okay, so the roof pendant xenolith falls into the hot magma and melts along its edge. Okay, so that's a cool thing. You can see this on the side of the road. These are hard things to find in real life, especially around New York. This is great. So anyway, so that's the first part of this. Oh, you got to turn. Go ahead. Okay, and so we got some ages on this, and they came up sharp as this comes up. 1006 plus or minus 5. We're right on the nose. So this means that all that mountain building I talked about, all the folding, had to have stopped by 1006. Okay, so that puts a nail on when did my collision stop. Had to have stopped by now. Okay, so these are nice, clean. You can see there's nothing on the outsides of them. They're nice, clean zircons. So that kind of puts the age on it. Next. However, all you have to do is walk down the street a little, and the diorite looks like this. Okay, and so the diorite came in, there was no deformation to it, and then something had to come across it later and deform it to make it look like that. Okay, and what it was this was a deep fault zone in the earth that it's called the shear zone or a myelinite zone, where it smeared out that rock after it was solid. Okay, so after that diorite was put into place, it got smeared out after 1005. Okay, and if you look at some of the close-ups of what the minerals look like that one up there, that's made like this. It shows you the direction that it actually moved. And so this, the San Andreas fault is what they call a strike slip fault. It's a transform. It's Los Angeles in 3 million years will become a twin city of San Francisco. Okay, so if you wait a little bit, there'll be twin cities. Okay, so because they're moving across like that. So basically it doesn't go up or down like those other things did. It just goes lateral. Okay, and so we looked at all of the indicators on here, but you can see that's where the picture is. This is kind of a, something off the internet to show you what it looks like. There you can kind of compare it to that black thing in the middle over there. And it tells us this was a fault that moved sideways after the diorite pluton came in at 1005. So we had the collision, and then everything started to slide sideways. Okay, and so that's how we can get the net. That's why this is all the same outcrop. That's why this is my Rosetta Stone. You can tell everything that happened in the whole park in one outcrop. Okay, so next. Okay, so here's what strikes the fault looks like on the surface. An offset strain. You can see the one over there is, that's if you went out to the San Andreas fault and you were in an active strike slip fault. The streams get offset. You get what are called sag ponds in the middle of it, so you get little wetlands along it and things like that. And everything is kind of offset by that. That's what it looks like on the map. In other areas, you can see that it isn't always quite so neat. You get openings that occur along these things, and once you get openings in faults, they can let fluids come up through them. So you can see on this other strike slip fault over here, where this is moved that way relative to that one, we get those blue zones where some fluids are kind of come up along the fault. Okay, and we're going to see what that does next. Okay, and here's kind of another picture of this is where it goes through Quartzofeldspathic gneiss, and you can see that like up in there, you can see that up in here, you can see that's kind of got the same rotation on it like that last one I showed you. These are also myelinites, shear zones. You can see in here too, it drags this way and drags off to the top is going this way, the bottom is going that way. That's why you've got that shape to it. That means the top going to the right, bottom going to the left. That's why we can see that that's a strike slip fault. Okay, and so that's in the Quartzofeldspathic gneiss. So it cuts across all the other units. The only one that's important is the diorite because it has an age constraint. Next. Okay, so where are these zones? So all of these like little, I don't know what those are, approximate signs in here are all strike slip faults. So you can see the arrows on each one shows you the direction. They're what are called right lateral faults, because you stand on one side, you look across, moves to your right, it's right lateral. So they're all of these little zones cutting through here are all strike slip faults. So they're all over the place. I mean, all over the park. They sit up on end, they cut across everything. So the reality is you're driving along, and as I said, you look out the window, if the rocks are on the side, you're looking at the old thing. If they're sitting upright, you're looking at the later stuff. Okay, so you can map Harriman State Park from your car. You don't even have to get out of the car. You just drive along. Oh yeah, that's basically the way it goes. Okay, so here's some of all these faults. They're all over the place. This represents a fair amount of movement. So we're talking about, maybe 50 to 100 kilometers of strike slip movement in the area after the mountain belt building. Next. Battery's running low. Okay. Okay, so the last thing I'll kind of take a look at is your plug it in.
All right, we'll figure it out. You can keep going.
Okay. Okay, so the last thing I want to do is take a look at these shears of these places where you get these mines. Okay, and this is Hogenkamp mine. Okay, anyone ever been to Hogenkamp mine?
Yeah.
Okay, so it's like a big corridor, right? You walk in there and it's like a long corridor. So why does it take on that shape, that corridor shape? You can see here's my class standing in the corridor, right? And you go in and all the magnetite is lined right up. Okay, so why on earth would that happen? Why would we line up all the magnetite like that? Next. Okay, so let's take a look at some of these mines. And if we look at them, all of a sudden a pattern shows up. So Hogenkamp is down here, right? And there's pine swamp up there, and they all line up right on. And here's these strike slip faults. They line right up. And if you go to the next one up there, you know, there's Surebridge mine and there's Bradley mine, and Bradley's on the top, but there's like 3 mines again. They line right up, and the mines line up. And the reason is because they're sitting right in the fault zones. So those fault zones opened up, the fluids came up through the fault zones and dumped all the magnetite into the fault. And that's why they are where they are. And that's why all of these mines line up, because otherwise there's no reason that they should line up. All right. And so that's the big thing. Fluids start going at great depth. They will go up any crack they can find, and faults are great cracks. Okay. So that's why we have 2 zones of magnetite mines up in middle of Harriman. Next. Okay, so you can look at how basically this starts out. We have the strikes of fault on the top. You drop to the next one, you can see they start to get a little bit, break stuff up. And then these little pockets open up inside of the mine, and they fill in with minerals in a progression. Okay, and I'm going to show you what that progression looks like. But you can see that's basically what's happening. So there's Hogenkamp and Pine Swamp. They line right up. They're along the same big fault pattern. They just 2 little gaps that formed in it, and the fluids came up and dumped everything into the fault. Next. Okay, and so what happens if you were to look at these things close? Here is the gneiss on the side. That's metavolcanic gneiss. What happens is you get this zone, which I call the bleach zone, because it turns white. Now, this is cut, so you don't see it go white. But here's the regular gneiss, it's kind of dark colored. Bang, you get that bleachy white stuff. And then all of a sudden, you get these layers of material filling in one after the other on top of that. So what basically is that? So these are each one of these are defined by different kinds of minerals. And then the magnetite's over here. Okay, so that starts first. And then you get this heavy duty magnetite coming in. And that's what occurs in all of these faults. So how do we make that? Next. Okay, so here's how it happens. The crack opens up, the fluid comes into it, it interacts with the edges around the crack, and it takes all the iron out of it. Okay, and then this fluid continues to move, and then we get these layers growing as the fluid changes all along, and in the middle you get the magnet. So the way you're gonna get it is this bleach zone where it sucked all the iron out of the rock, the fluid sucked it out, then it layered different minerals in here, and then the magnetite vein was in the middle. Okay, so again, it's still related to these strike slip faults. It's because the strike slip faults opened up and allowed this stuff to happen. Next. Okay, so ages of those things, we have the mineralization age, the metamorphic age, as we said, was in here. Metavolcanic rocks were up from, down to about 1100, 1050, well, 1100 basically, all the way up in there. That's their age. The metamorphic age is coming here 1050 to 10005. And then after that, that's when we get the mineralization. So we dated the mineral deposit, magnetite deposits, and that's what happens. Now, one more thing happens. Also along, oh, you also get folds. So remember, this is now shallower because it's been unearthed. So if you go up, and this is up on top, I can't remember what mountain that's sitting on right now, but you actually see some upright folds now. So the upright folds come later because there's been a lot of erosion, and you can still get these. These are related to the strike slip faults. Okay, so that is also that you can see. And I would have to see a map to tell you exactly what, I can't remember exactly the mountain it's on. Been a few years. Next. Last thing that happens in here is that we get the intrusion of these pegmatites. Okay, now these, and you can see these like these feather-like sprays. This one is right along with that 17K, I guess, right on the other side of the thruway there. And so these pegmatites coming right along the old faults. So after the magnetite comes in, then these pegmatites. The pegmatites come in as magma, but they have a lot of water in them, so they make very big mineral grains. Okay, and so you can see the size of these. Those sprays are this long. Okay, and you can see them right on the side of the highway there. And you can see they're so fragile that we had to have stopped the strike slip faulting by now. Okay, otherwise it would have broke those into pieces. Okay, so now we have a back end of the strike slip as well to say, okay, it had to stop by now. Go. And that's 990. Okay, so the strike slip only went from about 1005, right after the intrusion, to about 990 when the pegmatites came in. It was only during those 15 million years that you had the strike slip, and then the pegmatites, and everything stopped. And then nothing happened until, probably 500 million years ago. So it just went dead for another 500 million years. Next. Okay, so as I said, where's the basic summary is you had these volcanic arc, you had volcanic rocks, volcaniclastics means the sediments that come off of it. That happened from about 1150 to 1050 million years ago. At 1050, you had a collision with Amazonia. It's what is called the Renville orogeny. That's what the big thing is around here. That's the name you'll see. 1050 to about a billion. We had crustal thickening. The naps built it up. Granulite means the highest metamorphism you can get to. Started to melt. You got your granite sheets came in at the peak of metamorphism. The whole system stopped. At 10:05, you had the intrusion of the diorite. Then you had the strike slip faults, all of that stuff. The iron deposits came in. That happened from 1005 to 990, and then the pegmatites came in at 980. Everything stopped after that. So that's the entire sequence of everything you see in Harriman State Park, all the way over into Bear Mountain Park and over into Sterling Forest, all part of the same system. Next, I think that might be it. Oh, wait a minute. Shameless plug. Okay, since I have a nice captive audience, right? So I've written a couple of textbooks. I've written trade books and things like that. I'm trying my first popular book. Okay, so here it comes out in August 6th, and it's called Reclaiming Our Planet. They said I had first thing you want to write about something like that people care about. So it's on climate change. So basically, there's a lot of scary stuff on climate change. There's a lot of things people say, oh my God, we're dead. Other people say it's not happening. So this, I'm going to give you from a science point of view, what really is happening and what you could say, yeah, this is from climate change. No, that's a bunch of people who are trying to get me scared. And I'm going to go through all that. Then I put climate change into a context because we've had other bad things, environmental. Everybody kind of makes like this is the first time we've done something bad, right? Not the case. So I go through things like lead. Lead, we were like 2% away from the whole country being lead poisoned. It was that close. Okay, and now we have no lead, right? Except once in a while we get a little bit of, legacy lead, but that's it. So we got rid of it, we fixed it. We had DDT. It was so bad that women could not nurse babies in the 60s because they could give them a lethal dose. Okay, and now we don't have to worry about it. So we've had, and then I go through a bunch of them. We have a bunch of things, so there's a bunch of stories on where we started out things really bad and we managed to fix it. And in the end, I'm gonna go through all the stuff that we do now and what things we could do to defeat climate change. Climate change, 50 years, we could have it, fix it, but we gotta do it the right way. So if you wanna see what the right way is, looking from a completely unbiased, I don't have any political views on this, just unbiased view, it comes out in August. All right, so it's shameless, right? Okay, thank you.
All right, so we have some time for Q and A. If
All
you
right.
have questions, we have some potential questions from online participants as well.
Go
Is
ahead.
there any, piece of Africa in this mix? I've heard that parts of New England or something have.
I mean, you know, there are places that they've seen in New England, up in Eastern Canada, but not here. Okay, Africa collision was later. So that was a Paleozoic collision to help build Pangea. The Rodinian one was South America.
Was that the one that created the Appalachian?
Africa one made most of what you see. If you go to Pennsylvania, you see all those hills. That's from Africa interactions, yes. Go.
Are the mountains on the east side of the Hudson included in all of this? Like Breakneck Ridge, or is that a different?
You mean on the east side of the Hudson River?
Yes.
And it depends where. Some of it'll be the same, others, I'm not so sure, because you know, then it goes into another collision down to the southeast, the Tectonics. That's where you kind of go against them towards the east. So I can't say 100%, and certainly the stuff down in Westchester County is younger. Okay, so there's this kind of a band that goes through, and then there's stuff to the southeast of it that's a little younger.
So the band is like an edge.
Yes, it was straight up and all the way down to New Jersey. Yeah, go ahead.
Those faults that lined up all the iron mines in Harriman.
Yep.
Is that the same if you go the Sterling mine groups and down into Ringwood and then there was some mines south of Ringwood that scattered from, you know, but the big Ringwood mines, is that the same process with those faults?
Well, there in New Jersey alone, there are 440 abandoned iron mines. So, and they have come from a bunch of different ways.
Oh,
So
okay.
I'm not sure, I mean, the ones over in Sterling Forest, the Lake Mine in that area is not. Those are
Different
your
faults.
replacement, it's not on a fault. They're just replacement in the rock.
Oh.
These, when they line up like that, that's the fault.
Oh, okay, because I know Sterling, they're not,
Now, they don't line
not
up.
that, way.
No, right, exactly.
And Ringwood also.
Yes, probably. I haven't looked at that, but I have looked at Sterling. So, is there another? Yeah, go ahead.
Yeah, it's about the mines as well. but
Sure.
How did they originally find the iron? I
Yeah.
assume they didn't have a geologist,
Now,
right? And were they smart enough that they knew that there was one here, they could predict that they could move up and sort of follow that?
right, so
fault?
you asked a good question there. So, I wanted to have them do this over in Bear Mountain. But in the old days, what they had was called a dip needle. Okay, and the dip needle was a magnetic needle this long, and they would walk around the woods with the magnetic needle. And when it pointed down, you had magnetite, because magnetite is with the iron and it's all magnetic. That's how they found the magnetite in the early days. And then they would start digging and see if there was enough there worth mining. Yes.
A little farther afield from Harriman, but you
Mhm.
mentioned Franklin and we live near there and have been to some of the mines and the museums and some of, I understand the minerals are unique in Newark.
They are.
Can you explain a little bit how that came to be?
So the question is on the Franklin marble, which is to the west of here. That whole area in Franklin is filled with marble. And in fact, I wrote an article for them last spring on the tectonics of the whole thing. So you can look at that, and they have a monthly newsletter. So it's in the newsletter in the spring, so you can see it there. But the deal with that is that it was in a marble, and it looks like they were in faults as well. And these fluids came up, and they had they brought in all these strange elements. And because, that's where they used to get all the lime, from, so that stuff is extremely reactive. And it reacted with these fluids and produced these minerals that you can't find anyplace else in the world. Now, it's supposedly from a pluton that was, crystallizing and letting off water, and that's what interacted to make those strange minerals. But yeah, I mean, it's a one in world place.
Thank you.
Yep. Go ahead.
Hi, I have two questions.
Sure.
What is the map that you have on slide 2?
The maps of these geology maps?
Yeah.
Well, there's two of them. I mean, they're all part of they're open file reports at the New York State Geological Survey. Two of them are online. Okay, so if you look online and, it's Gates and Valentino, if you look online for one of those maps or email me, I can send you the link. But you can actually get two of the maps are online. I think the Monroe Quad is online, and maybe it's the Sloatsburg Quad. But I think those are the only two they have up. The rest of them, you would have to go up to Albany to get.
So my
Yeah.
question really is about the volcanic gneiss.
Mhm.
How can you tell the difference between volcanic gneiss and one from a granite?
Well, the granite, so the volcanic rocks were very dark in color. Okay, so the minerals that you have in there are dark colored minerals. Granite, even though you go to Home Depot and they say, oh, look at all the granite, only the white colored stuff is granite. Everything else is something else. But even though they tell you it's all granite. So granite has to be white in color by definition. Anything else, the volcanic rocks, and the granite usually is not layered. So these you can see are strongly banded, layered, and the minerals in them are dark colored minerals. So once we took that out and ran it, the chemistry of it, it plots perfectly as a volcanic rock and from an island rock. So it's the chemistry that helped us.
I'm walking around Pyramid Mountain in Morris County,
Mhm.
and I'm telling people that the gneiss is there from a granite.
Could be.
Okay.
I can't tell you. I mean, I've been to Pyramid Mountain, but it was to take my kids hiking. So I really didn't look at the rocks that much. So, sorry. Next,
I
yeah.
have another question about the iron. So it opened up where the magma came up, because it's mostly iron way down, right? Yeah.
The iron, what they think is that when you get these, what they call black smokers, you get them in the ocean and they spew out stuff. And so you get kind of layers that are more iron rich and less iron rich. And that's what you start off with. So the iron's not that dense. It's not all iron. It's just kind of iron rich. You take the fluids, you flush them through, they interact with the rocks, and they basically dissolve out the iron and carry it up in the fluids.
Well, but my question is this,
Hmm.
those mines up there at the time, yes, it was economical to a certain extent, and then, it petered out. There weren't such big deposits to make it, except for the Ringwood mines were a lot more. But why did it keep coming up? In other words, why was it such small deposits if there was so much down below, and what caused it to close it off? Is it just natural movement?
It was,
It came up and.
yeah, I mean, at a certain point, these things, it was all the stuff, the hot fluid and stuff like that, the fluids cooled down, the rocks erode, it comes up. I mean, there is really a lot more iron left in the rocks up in here, but the problem is that in the late 1800s, they discovered the Mesabi range in Minnesota, where you could basically shovel the iron off of the surface, and it became uneconomic because you had to mine it here, didn't have to mine it there.
Yeah.
So that's really why we stopped. I mean, they picked up mining back in the 70s. Down in Mine Hill, New Jersey. It was in the 1970s. They were still mining iron. So it was economic then. I mean, it could be economic now, but how much is your house worth? How you could really are people really gonna buy a piece of property that a house is sitting on to mine out a couple $1,000s worth of iron? That's the problem. Yeah.
At what point did the Hudson River come in? Was that a fault zone for contents?
Well, I mean, they think there could be a fault under the Hudson River, But it's, that mostly is, all of that steep slopes were all glacial. So that happened between 22,000 and 12,000 years ago. Yeah, so that's more recent. And those are actually considered fjords. Yeah, so it's that, and they're, the deepest point is 200 feet below sea level in one part, in the bed of the Hudson. So, because of the glaciers, the sea level dropped 200 feet. And, this little lazy Hudson River turned into the Colorado River for a while, so. Next, Jack.
All right,
Go ahead.
another
Yeah,
slightly
sure.
off-topic question.
That's okay.
You mentioned the erratics, the boulders.
Yeah.
And I've always wondered, is it possible to determine where those, from the minerals, where they originated from, how far they traveled?
Yeah, absolutely. There's been some studies like that.
Oh,
Certainly, if you walk up in Harriman and you see this pudding stone sitting there,
yes, right.
pudding stone didn't come from there. It came from up in the, the Swan gunks, the gunks.
Uh-huh.
And then it was transported, however many miles south and then dropped. And so there have been studies on these, even though you think, well, everybody said, well, all those rocks came from Canada. Most of them move less than 10 miles. Yeah, and then they really move that far.
Very interesting.
Yes. Yeah, go ahead.
Two online questions.
Sure.
One is evidence of glacial activity in Harriman State Park and the impact on the stones that you were talking about before.
Yeah, so, yeah, absolutely. We had, 12,000, from 22 to 12,000 years ago, we had glaciers that extended all the way to about Morristown. Okay, and up in Harriman, up where we're here, they're about a mile thick. By the time they get down to New York City, they're about 2,000 feet thick. So these were big, thick things. They scraped everything off the top of the hills. So the reason you can go, you go like hiking down there and you go to the Torn or, whatever, I think the Timp maybe, where you get on the top and it's just bald on the top, that's because the glacier, cleaned it up. And so the other thing you get from the glaciers is that because, all the rocks on the bottom were rolled underneath this mile thick sheet of ice. So they were all wound up round. Okay, so if you see rounded rocks, they had to have been there before the glacier. Anything that's angular means that it came after the glacier. And so you can see before and after, because of that glacial impact. Was there anything else they wanted on the
The other
glacier?
question is, east of the Hudson Mountains, maybe different collision than Harriman State Parks.
The Hudson Mountains?
East of the Hudson.
East of the Hudson. Well, as I said, the east side, you go to New York City and you go to, the rocks that come up from into Westchester and things like that. And those are from what is called the Tectonic orogeny. So that happened about 450 million years ago. And that's when most of those rocks were cooked. And so like the Manhattan schist, you go down to Central Park in Manhattan, that stuff is all from when the pack collision was taking place between two colliding continents about 450 million years ago. So that's a later event. Go.
Is the Champlain thrust a ripple of this event?
Champlain thrust is younger,
Okay,
so.
as in the 500 million ago?
Yeah, more like, something that occurred during the Paleozoic. So the after, I have to go and look and say exactly what it was. I've been up in that area, but, I can't remember. It was a long time ago. So I can't remember exactly which one that went into, but that's a later event for sure. Anyone else?
So is this one of the oldest rocks on Earth here in Harriman?
No, you go to Australia and Africa, the cratons in there, even in the middle of Canada. These were the really old continents. So in there, they have things, 2.83 billion years old, 3.5 billion years old, things like that. Those are the oldest, so those central parts of these continents are the oldest rocks. But, to have some erosion stuff coming from 2.8 billion years old, those are old, that's old parts of rocks that we have over by Perkins Tower. Yeah.
So if the area of Harriman was originally Amazon, What about the area just west of Harriman, like the Hudson, the New Jersey Highlands, were they also Amazon or something?
Well, the Amazon came in and kind of crashed to the east of us here. So we come back to the New Jersey Highlands, and so we have a piece of what I just talked about, but then there's an older group of rocks that are behind that. So if you look at like the Franklin Marble that we talked about, the stuff in the western part of New Jersey, that's 1.3 to 1.4 billion. And as I said, I wrote a little piece and they have the, whatever it is, the Franklin Museum, or whatever. They put out a quarterly thing. So I wrote a history of the tectonics of that in there as well. So, but that's old, that's another, that's the first piece that was put on in North America during this buildup of Rodinia. This that we have here is the second and biggest piece.
Does this same geology continue west of Greenwood Lake? Is that the same geology?
I mean, Greenwood is in the, has the, that's sedimentary rocks. So there's the later sedimentary rocks, the Belleville sandstone,
Right.
named for Belleville Mountain and stuff like that. That goes all the way down under Greenwood Lake. This stuff goes south. So you go to the Blue Ridge, and this is the same age as the Blue Ridge Mountains, and all the way to, all the way down to the Great Smokies, and all the way up to New England. This is part of the same. This is that Renville thing, but we have just like the best view of it of any place. They have to come up here to see what the good stuff is. Anybody else?
One more online question.
Sure.
What causes the mountains to erode so much over the years? Like, why is the Greenville so low now?
Well, so in the Himalayas, right? The Himalayas are actually rising still, because this collision is still going on. They're rising at 5 millimeters a year and eroding at 4 millimeters a year. So they actually are only going up 1 millimeter a year. So when you get things up high, they erode fast. Okay, now, as they get lower and lower, the erosion slows down. But think about it, you had 500 million years in that time for these things to erode down. 500 million years is a long time, So even that, no matter how fast or slow, you say, it had plenty of time to go to erode away.
You mentioned your Rosetta Stone and a couple of
Yeah.
other areas in the park.
Yeah.
For people hiking in the park, any particular trail that has the best geology to look at versus another?
Yeah, I'm gonna have to get one of the maps. I have to
Okay.
update my maps anyway, so I'll probably buy some maps before I leave.
Okay.
But there's some, I mean, down in that central part, right around Lake Tirati, that is where that one place that I saw.
Oh, that's right. Okay.
There's when you go up by the Hogenkamp mine, and I can't remember what trail goes past the Hogenkamp mine, but if you go in there and then you go up the hill on the top of the ridge over there, there's some great stuff. So, I mean, as far as seeing things, you can see the mine and there's great minerals you can find in that mine too. And then up the hill, and then you can see that big fold I showed you was up on the top of the hill there. So that's a great place to go. That's why I always used to take people a lot.
Okay, thanks.
So, yeah. Yeah, go ahead.
Are there any geologists in the Amazon who found similar rocks?
Yeah, I mean, that's what we did. We looked at what other people had looked at in the, because we don't know what AG Amazon is. So we had to read literature about what the geologists had found in the Amazon and Amazonia that we could then correlate with ours. So yeah, there's plenty of studies down there that we can use to say, yeah, this is the same rock.
What part of the Amazon country?
Not sure. I look at this, this stuff is, I've been doing lots of other stuff since this. So I mapped this, all of mapping you saw, I did mostly in the late 90s through the early 2000s. So you say, oh, you remember that? That was 20 years ago. Maybe.
My husband was really like.
We're recording this as we speak, so it'll be up on YouTube, the whole presentation.
That's good to know.
Yeah, so you can watch anytime. So if I made a mistake, you can catch me anytime you want. You're like, hey, you said. Right. I'll be used to it. Yeah, go ahead.
The Hudson River Railroad was built in 1850 up the east side of the Hudson River.
Mhm.
From New York City up to Albany. And it was purposely built 5 feet above high tide. It hasn't been raised since then, 1850. Do you know if there are plans to raise it in the future?
I have no idea. Nope. I know that they're using it now for the, they started bringing down that Bakken oil down on the east side. So whereas I used to be able to take my classes and go look at the rocks on the railroad, they now have people who will arrest me if I try. So you can't go look at the rocks on the railroad on the east side of the Hudson anymore. That's all I can tell you. The cops chased me off last time I was there. And luckily I was fast enough. Anyone else? Yeah, go ahead.
I think there used to be some copper mining in northern New Jersey, but not much. I mean, it
Yeah.
had no relationship to the iron mine.
No, that's part of the Newark Basin. There was some copper mining, what was it called? Patterson Plank Road used to be used to haul copper out of the mines in there. So that's related to the Palisade Sill, when it came, which is an igneous body as well. When it came up into the rock, then you basically, instead of iron, you mobilized copper and made copper deposits. So that is from, which Rockland County all sits on what's called the Newark Basin. So the east side of Newark Basin has some copper mines in it.
That's only about 100 million years old, right?
They're probably more like about 200, really. So when those were, but there wasn't, the deposits weren't big. I mean, the deposits here were huge. I mean, most of colonial America got their iron from the highlands here. I mean, other places didn't have near as much as this. So these are big deposits.
Palisades, I assume that was a different geology than Harriman.
Yes.
It was all about with volcanic, or that was something.
They fed after you got Pangea. So Pangea then started to break apart. As I said, the supercontinents put together, they come apart. So Africa was nailed up against North America. So, and then as it broke apart, as it split apart, then you develop what's called the Newark Basin and all those red rocks that you see in there. And also you had these magmas will come up as you're breaking it up. And so the Palisade Sill was a feeder of magma, which came out on the surface as volcanics, which are called the Watchungs. So if you get out of New Jersey, all those layers of Watchung were volcanic flows that came out of the Palisade Sill feeding up to the surface, the volcanoes.
Because I think there's along the Jersey Turnpike, there's a remnant of a volcanic called Dara.
Yeah. Right down, what's it called? Snake Hill.
Yeah.
So it's right on the east spur of the New Jersey Turnpike. Yep, in the Meadowlands. Yes. Anything else? Nothing about earthquakes or anything?
I was gonna ask you about I heard, maybe it was you, or somebody said it wasn't the Ramapo Fault.
That was me.
That was you, okay.
Right. So I have a graduate student, we worked on this a decade ago, but he's lazy. Otherwise it would have been published by now. It should have been. So I got on his case and said, you better start, I want this out by Monday. So hopefully it'll be out by Monday, but it does, you could, if you go online, you can see in the US Geological Survey, the Ramapo Fault goes northeast, right? Goes this way. You look at all those aftershocks, they go this way. So it can't be the Ramapo. As I said, I've mapped the faults. There's one that goes right through along the, what is it called? It used to be called the Quickway, but it's 84, right through Monroe. It has had like 5 or 6 earthquakes on it, and you can walk out the fault. You can see where the offset was on it. And then there's one in the middle of Harriman. If you go on Little Long Pond, it goes right along there, and then it goes up onto Rock House Mountain, which has rubble that's all angular, because it was all from that was a cliff from earthquakes. and it dropped all the rocks off. So those are active faults in the park. And that's what that's what generates the earthquakes. Those guys at Columbia University, Lamont, who sit in front of computers all day and don't go outside, are the ones that said it's in there. If they went outside, they would find out that there's not the Ramapo fault.
Yeah, I saw those blaming Ramapo.
This earthquake's epicenter was down in Lebanon, New
Yes,
Jersey.
yeah.
So that's in the Newark Basin, right?
On the edge. I think it's right up against, so a lot of the aftershocks go across into the highlands.
So is it fault perpendicular to the Ramapo? That
Yes.
cuts from the highlands
Yes.
into the.
Right, and it's gonna come out and then we'll be scooped on it if my graduate student doesn't get the work. But we'd have them all mapped, they all like that. You know, in fact, there's an active fault in New York City. It's called the 125th Street fault, goes right across 125th Street. So they go east-west, or, you know, a little bit northwest, that's it, that's the way the active faults go. And it had like 2 or 3 earthquakes on in like 2002 or something like that, right after 9/11. There's a bunch of earthquakes on that fault. Those are the active faults. So, but I've been arguing with those guys for a decade.
How did they interview you on it? PR?
Well, they interviewed me on NYC. I was on for like 10 minutes, and I said, it's not the Ramapo. I tell everyone, it's not the Ramapo's dead. You know, it was active 200 million years ago. It's not active anymore. Okay. So you guys know now. Yeah.
Don't have a name?
No.
The other one.
Nope.
That's the.
I only named the faults I could see. So the ones down there, you can't really see that well. You know, the glacial line came down to about Morristown, and then there was just all this glacial outwash that dumped everywhere. So you really can't see through it that well. Up here, everything's scraped nice and clean, so I can show, you can look on Google Earth and see those faults cut right across everything. So you can actually see them. So you can have them up here too. You know, we've had a couple, the last, you know, there's been, I guess this is like the 4th big fall. The last one was probably bigger, was up in, it was offshore in Jamaica Bay. And that one, they estimated at a 5.3, 5.4, but probably was bigger than that because it did some damage. You know, it didn't kill anybody. It damaged a lot of stuff. So I think this one, you know, 4.8, and it really didn't do any damage. You know, it was cool when it came through the house, but it didn't do any damage. So I think that one must have been a lot bigger.
What year was that?
1884. You know, and of course, what did Columbia University people say? What fault you think they said it was on? They said, oh, it's Ramapo. It's not Jamaica Bay, you know, come on. So, everything's a Ramapo. It's, you know, because they want it to look like the San Andreas fault. You know, San Andreas, Ramapo. Yeah, go ahead.
The earthquake, I noticed for similar reports, like sometimes, areas closest to the earthquake, people don't feel it, and get sometimes I was hearing people hundreds of miles away, they feel it. And why is that?
All right, so it's, you know, clearly the energy is highest right above the earthquake. That's called the epicenter. Focus is where the earthquake goes off, epicenter on top of it. And the waves spread out like if you threw a rock in a pond, they go out. The problem is on water, it's all the same. But on rock is not all the same. So it's basically the same as if I banged this table and what happened. And if I took a bowl of Jello and banged that, what would be the difference? So some rocks behave like Jello. Those you got to be careful with. So a lot of people down in the southern part of New Jersey actually felt it more than people closer to the earthquake. Because the stuff down there is unconsolidated. It's, you know, muds and sand, so it shakes.
And it was felt as far north as Salisbury, Vermont,
Yep.
at the north end of the Tectonic crust.
Right, but it's the hard rock all the way, so it can transmit a long distance. It just doesn't do that much damage when it's in the hard rocks. And the soft stuff, you know, I mean, it's like in the, you know, the Loma Prieta earthquake in 1989, the one during the World Series. And they had this marina district that was made of fill. it just destroyed everything there. Other places were okay, but any place that's made of fill, you got problems. So,